Writing code is hard, especially because sometimes when you're writing a library, you're defining an API. You don't really know what you're accepting because you're trying to be as lousy as possible and less strict in your API. And that's really hard when you're dealing with code, let alone when you're getting bytes from a stream. Turning byte streams into structured data is one of the hardest things I've ever had to do, and everyone, even very well-seasoned programmers, get this wrong all the time. And I know that because I work in security, and most of the bugs depend on deserialization issues. The only thing that people get wrong more than these is writing regular expressions, and the worst is when they do both at the same time. So, most of my talk is going to be about an exercise, which seems very simple, but believe me, it's not, because it took me a while to get it right. The exercise is the following. I'm going to try and match a string against a constraint. I'm going to accept a sequence of A, B, and C letters in this order, and they all have to be the same amount. This seems like the simplest language ever heard of, but the problem is this is a context-sensitive grammar. It's not exactly the easiest thing that you can parse. These are some examples of things that we will be dealing with. Now, of course, my first attempt was to use Ruby and regular expressions. Did I manage? Yes. Do I like this? Oh, so much. Would I ever put this in production? Not in a million years. Why? Well, have you looked at it? But also, the problem with these kind of things is that it's a write once, read never kind of approach. Maybe you can get it to work, and yes, this works because I've tested it against the rest of the code, but I wouldn't wish this to anyone, especially not me in the future, to try and maintain this behemoth. Now, there are some use cases for regular expressions. Don't get me wrong, there is a reason they are in the language. But they are for stuff that you don't know when you compile your code. If you have regular expressions in your source codes, I would take a look at them and wonder, can I write code that does this better? For two reasons. First, it's easier to debug code than debug regular expressions. And second, it's going to probably perform better because regular expressions are not natively compiled, especially in Go. So you will need to compile them at runtime and execute an automaton. And you never want to spend an afternoon trying to debug a regular expression that doesn't work. And you could ask that to Cloudflare, for example, because they went down for a few hours because of that. So I'll switch to the actual solution, the first one that I could come up with. So I have basically three states. When I'm reading A, I increment a counter. When I'm reading B, or any other letter, I increment another counter. And when I switch from one letter to the other, except for the first time, I check that the counts are all the same. This loop is the smallest piece of code that I could come up with, and I tried with a couple of inputs. It works kind of okay. I hate it with all of myself. Not as much as regular expressions, that's very hard to beat. But this kind of code is iffy. And yet still, this is the most common solution that I find. When I see a vulnerability in my job that is due to deserialization is because there is some sort of code that was written like this behind it. And the reason is, it's so hard to reason about it. This code has been on the slide for, I think, about 45 seconds, and I'm pretty sure that none of you has found the bug. And the reason is, this code is practically impossible to debug by just looking at it, because it's hard to follow the state. You are in a certain situation in a loop, but then you switch on other states that are unrelated to that loop. You're trying to parse the syntax and logic and constraints at the same time. The bug is in the return, like in the last line. So this is an automaton that basically checks that the string is correct so far. But when the loop is done processing the input, it just says, OK, this was a good string, but it doesn't check if it was long enough. Now, this might seem trivial, and in this case it is, but one of the latest vulnerabilities that I found in actual production code was something like that. There was a validator that would just say, OK, it's valid so far, but they implied that the string was in and of itself fully valid. To approach this problem, the best thing you can do is to separate two things. First, tokenize. This is just a simple example. Don't look too much into it. So take the string and produce structured data. And then you assert properties on that structured data. So in this case, even if you don't know what the code of tokenize does, you see that I say, hey, I need that amount of tokens for the string to be correct. And also, I need all tokens to contain this data point. So reading this code is much easier, and usually if there is a bug is in the tokenizer at this point, the constraints are pretty easy to express. Now, doing this by hand still has some shortcomings, because you're all happy about your code, and then someone arrives and they're like, but is it streaming? And you'll be like, what do you mean by streaming? Yeah, I'm about to feed 4 yottabytes of data into these things. Can you process that? And you'll be like, how much money are you willing? No, okay, I'm going to do a streaming API. So dealing with streams is hard, especially when you have to deal with IO reader and IO writer, because you need to manage buffers. And if you haven't received enough data, you need to deal with complex things. For this, the standard library can help you a lot. There is a type in the buff.io package, which is scanner, to which you can pass an arbitrary split func. By default, this is going to split lines. You probably have used this in some simple exercises to read from the command line. It's really nice because it splits lines regardless if they come from the correct version of the ones that uses carriage return. And when you use that, you don't know that you're, for example, discarding some characters. This is a really nice API because, for example, when you use it, you do something like that. So you create a new scanner for your stream, pass it a splitter function, and then you just scan, read the text, handle the error if any. Now, in this case, the splitter for our tokens is quite trivial because I just check that if I change the letter, I emit the token. So the output of this thing is going to be all the A, all the B, all the C's. 3 tokens. This is a simple language, as I said, but this is already much more readable when you look at it because you have a part that does the scan and a part that deals with the tokens. In this case, reading the tokens is done with, like I did it with bytes because it's faster. You don't have to if you are dealing with strings or something complex. You might want to call the text method of the scanner. It's going to do an allocation, but if you don't care about performance, maybe dealing with a string is much easier, especially because you don't have to do this kind of low-level calls into the code in Unicode. At this point, you might say, yeah, but Rob, ABC, really? That's not a real use case. And I would be like, yeah, but 25 minutes, come on, cut me some slack. But also, there are some other approaches that we can use that can address basically any arbitrary complex language. Rob Pike gave a 1-hour-long talk on this specific approach. I can't embed it all. I will try to summarize some of it when the input is very well defined. When the input is not very well defined, Anna Bernardi gave a talk at GoLab in 2018 on how to create a state machine that doesn't really know in which state it is. Like, it needs to kind of guess which state is it going to be in. So there are some approaches to this that I'm going to try and use for this simple language. My mistake in the first try was to try and do everything in the same loop. But clearly, what we are dealing with is a state machine that has different situations. The first one, we are counting the A's. And this is what we want to do from now on, reach that count with the B and the C. When we are in the B state, it's not sufficient to just match the A count. We need to also read the C's. And then C is the one that can finally say, OK, we're done. The problem is solved. Now, those 3 states look the same when you looked at the problem the first time, but they're actually 3 different states. So the best way to write code that addresses these kind of situations is to split it up. Now, for this simple example, maybe it's not exactly needed, but I wanted to show you how it's done. The best approach that I prefer, and by the way, this is the only piece of code that I could write while working on this talk that didn't have bugs the first time I wrote it. So this is the only one that I got right on the first try. You create functions that are states that take a cursor, that could be anything, in this case it's just a wrapper for the input, and return the next state and an error, or in this case, since it is so simple, just a Boolean. What I did is I created 3 of those. The A state counts, and if finds a B, returns the next state, the B state. The B state checks for B's, and if it finds a C, or if it finds something that is not a C, it breaks. Otherwise, it returns the C state. And the C state, well, you might have guessed, counts the C, and then it checks that the count is correct. Now, the state machine, while it runs, is beautiful. I think that this loop is amazing because you start with an initial state, And then you loop on the state machine, asking to every state, can you give me the next one until there are no more? When you're done, the state is going to be nil, and the error is going to be nil, or the Boolean in this case is going to be whatever you decide to put in it. This approach is very reliable. Like, it's efficient. I know that some inlining cannot be done by the compiler because you're passing functions around, but in my experience, this doesn't affect performance that much. It's simple to write. You can shut down your brain and focus on a state at a time. So you can write unit test for every state, which to count A letters is not that needed, but sometimes you're parsing other things. For example, a text template library in Go is written with this approach. So all of the actions in your templates are parsed by these. And in that case, you want to write a unit test for every state that you're in, probably. Again, it's simple to write. It's easy to test. It's easy to maintain, because sometimes you find a bug in a state, you just fix that state. You don't have to meddle with counters that are shared across states. You know the state is not shared because you have that cursor wrapper that only exposes very well-defined APIs. Also, it's common. A lot of libraries in the standard library expose some sort of tokenizer that you can rely on. So if you get used in your mind to approach problems this way, you will probably have an easier time every time you have to do something similar. Once I had to create a library that takes an HTML template and rewrites it to add some attributes to some specific HTML tags, it took me 10 minutes because there was a tokenizer for HTML in the standard library, and I've written like a bajillion examples of these kind of streams. So if you get used to this, it makes your life easier. And also, if you need parallelization, because sometimes you parse and you need to do something with what you parsed, you can do it in parallel. Because instead of producing a slice of tokens, you can produce a channel of tokens. So you can, it's not my day. So, as I was saying, you can return a channel of tokens so that you can process the data that you just parsed while you parse the next bit of data. When testing is involved, I see a lot of people do this, not wrong, but insufficiently. Fuzzing is something that I don't see adopted enough in Go, especially for these bits of code. If you have a byte stream that needs to become structured data and you don't have a fuzz test, I can assure you, you have a bug. You don't know about it, but the bug sure does. So the simple example of fuzz that I can create is I just add all of my unit test cases to the fuzzer to instruct what to fuzz for, and then I just call the function. The only thing this is going to be helpful for is to find out if your function panics. It's already something, like panics are bad generally, but you can also assert other things. For my specific language, I can say if a string got accepted as correct, and it wasn't long, exactly a module 3 amount of letters, it has to be a bug. Like I know that the input has to be long 3 times the base string for this language. But the best value that you get is from differential fuzzing. If you have 2 implementations of the same thing, and this could be 2 different versions of your software, call both of them and check if they agree. If let's say that you have a competitor that is writing a library that does exactly what you do, import them, check if they do the same thing that you do. Once I wanted to fuzz an HTTP implementation that is in the wild, it's called fast HTTP, and I wanted to check if it is actually, why is it faster than the standard library implementation, because back then I was maintaining the security part of it. And I realized the reason it's faster is because it's wrong. It doesn't implement the full HTTP specification, and that makes it very easy to go faster. The way I found it is because I just called both libraries and asked them, how did you parse this input? And the answer was that one was parsing it almost correctly. I found a couple of bugs in the HTTP standard library, but I found 36 bugs in the fast HTTP package because it didn't implement the HTTP spec. It's intended, it's in their documentation, but it took me like half a minute to find the bug. So differential fuzzing allows you to find bugs without knowing what you're fuzzing. Now, unit tests are not just there to test that your code works. you just wrote it. There is a good chance it works because the problem is fresh in your mind. Unit tests are there for you and your team so that they can change your code, meddle with it, and make sure that they didn't break anything. I've seen a lot of code bases fail to grow because they didn't have unit tests. Your code is probably correct. I mean, if you put enough attention to it, it's very, I wouldn't say it's easy, but it's very straightforward to try and build something robust. But unit tests are also there to make sure that your code keeps working. And fuzzing is the thing that guarantees that edge cases will be found if new ones appear. Now, I'm going to do a real-world example of something that I did recently with some of these approaches. Now, how many here wrote something that is web-related, like either a web application, a web server, or something like that? Wow, didn't expect that much. So one of the things that is lacking in the web platform is that the server cannot push data to the client. Usually you either end up pulling it or you open a WebSocket to the server. Or so I thought. I actually found out that there is a way to push data from the server to the client. It's called server-side events. And it's a very simple specification, basically to the point where it fits a slide. You can create a response which is event stream, and then just write messages that are separated by a couple of new lines. It also accepts comments if the line starts with a colon, and that's it. You can just flash messages to the client, and the client will get an event fired in the window context. Now, I wanted to create an API for a client for this thing, which is just something that returns this. So I don't know how many of you have gotten the update on the 1.23 version of Go, but they introduce that, and we will see later why that is useful. So for this problem, I decided to use the scanner because I didn't need a state machine to just split lines. So I copied the standard library implementation to scan lines, and I just added one more new line because the specification requires me to look for a double new line. So I just copy-pasted the scan lines version from the standard library, and that's the bold text is the stuff that I changed, basically. So that was super easy. Copy-paste, and you're done. And then the parse is also very easy because I looked for a colon, and I would just split the string on the colon. I didn't even need to call a string split because I could just find the first index of colon and then create the message. One thing that people forget about in this point is that they fail to propagate errors correctly, or they don't know what to do with errors. In this case, at the parse stage, you need to forward them. Usually, when you are in the parser, you don't have enough context to decide what to do with this error, because maybe the client wants to keep going, like you want to keep accepting messages even if one was broken. Sometimes that can corrupt the logic of the server, so you don't want to. So forward the problem, both from the scanner and the parser. You could just bubble up the problems, and you be, for example, very clear by wrapping the errors in saying where the error happened, either in the scanner part or in the parser part. The beautiful thing about reasoning about parsing and accepting input in this streamed way, either with a state machine if the language is complex, or with a scanner, or something like this, is that then the usage of this API, the consumers of this API, can just range over it. Like in this case, the library that I created allows you to do this loop. So range SSA.parse of the response body, and you can just loop. Every time a new message arrives, your loop is going to do another round, and then you just decide whether the error is critical enough to abort or keep going. And in case I wanted to handle cancellation or stuff like that, I can just put it in the loop body. And in case I wanted to parallelize parsing of messages or buffer them while I'm processing them, I just use a channel instead of an iterator, and that will allow me to have a Go routine that processes the messages and one that is busy buffering and reading them. Also, the buffering is hidden by the scanner, so I don't really need to do much about that. So, brief recap. The approach, the safe and sound approach to this kind of problems is split the problems on several layers. If the problem is too complex in and of itself, tokenize, and then on the upper layers decide whether you need a state machine or something simpler or something more complex. The thing is, every layer should be self-contained enough to write unit tests for it and fuzz tests for it where it makes sense. If you have an API that takes a string and returns an object, there is a good chance you need a fuzzer for that. Try to hide complexity to the user, but provide handles and knobs to the people that want to go deep into that. Because, for example, one thing that I love about the text template package is that it exposes the parser. So if you want to extend the language or, like in my case, modify a template before you actually execute it, you can, because they provided me with the methods to do so. Now, there is one last approach to this kind of problems, which is to create the parser with a generator. There are generators in which you define the parser in a language that you have to learn and your team has to learn and maintain, and that produces Go, and you know that Go, sometimes it's even proven to be correct if the source is correct. Now, this has a lot of, it's a steep entry barrier because you need to learn a new language. And sometimes some people might be tempted to modify the generated code, and that also took down Cloudflare. So apparently you tried everything over there. So this is the recap slide, and this is me thanking you for your attention.
Thank you. So you said that you enjoy playing dangerous games, so you said you want questions from the audience. Do you still believe that?
Yeah, go for it. Any questions? I don't mind if they're harsh.
Questions?
I have a question there.
Where is it? Wait for the microphone. Two microphones converging. Who's getting there first? Ha!
Just a small question. On one of the first slides, you mentioned that it will be recommended only to use regular expressions for patterns that are unknown at compile time. Can you elaborate on that? I mean, which use cases would imply you would use regular expressions on patterns that you don't know?
Yeah.
Would you build them when necessary?
Yeah, what I meant by that is, let's say that you have, I don't know, a cloud text editor, and you want to allow your users to specify search patterns in their text. You get a regex from them, and you run it on your machine on their input. So there is a chance for you to use regular expressions when your users need to specify search patterns. Like, that's a thing. But if you have too many regular expressions or like complex regular expressions in the source code for your server, good chance is you have a very well-defined input and you know how to parse it, but you didn't want to go to the extent of writing the code, which means you wrote something that you think it looks right, kinda, and you hope that it actually does what you think it does. That's why I'm generally against regular expression sources.
Excellent. Any more questions? In the meantime, the next speaker can get set up. One back there, and then I'll be back here.
Nice talk. Thanks. Do we have a microphone? I can repeat the question. Yeah, okay. So, scream.
Okay, I have seen cases where a parser takes too much time and it never finishes. Do you think the time has come to put context and timeouts in parsing unknown inputs?
Yeah, so if you parse unknown input, right, the question is, if you parse unknown input, the processing could run forever because it's a known input and it could actually be an exploit, not actually trusted data. So should you put a context on parsing to have a deadline? Yeah, I don't think you need a full context. You can just pass a channel with a timer that expires because you don't need the full context API there. But yeah, sometimes when you accept untrusted input, you should create a memory bound and a time bound. And for the memory bound, it's super easy because in the I/O package, there is a limit reader function that takes a reader and returns a reader that stops at that length. So to modify this code, you just need to pass a limit reader to the scanner and you're done. But yeah, if you accept arbitrary and trusted input, please limit it. Thanks for the question. We have another question. Do we have time for another question? I think.
Yep, one more.
When you said about fuzzing, that differential fuzzing is the best kind of fuzzing, I sort of agree, but at the same time, if you have an existing implementation and you don't have a second one and doing that is costly, surely that's not the next, like the best step to take.
rewriting your entire code base with different people to just allow differential fuzzing is not the best idea. Like if it is available, like if a second implementation is available, use it. If you don't have one, fuzzing is what you have to deal with. And like assert strong constraints. For example, in my case, make sure that the string only contains A, B, and C. That is long, like 3 times the count of A, for example, which is much easier to implement. And I think there was also another question there.
A few years ago, you said that you were going to use Ruby regular expressions to validate a Go program. Whatever happened?
So, Ruby regular expressions are fun to play with. I wouldn't say that it's something that I would suggest anyone to get started with. And if the syntax is not the best, people can also use Ruby regular expressions, Perl regular expressions. But don't. Like, that thing is so broken. Like, just, that's not a question, that's an invite to madness.
Excellent. All right. Thank you very much. Another applause for Roberto Clapis.